Hello, this video will start chapter 2, which is on atoms and the periodic table, and we will go over section 2.1. So this first section is on elements, and we learned in chapter 1 that an element is a pure substance that cannot be broken down into simpler substances by a chemical reaction. And so elements are represented, are arranged in the periodic table. And so because of that, you want to have the periodic table out. A paper copy is preferable, but you want to have the periodic table available. And so you will see from the periodic table that elements are represented by a 1 or 2 letter symbol. And the first letter is always a capital letter, and the second letter, if there is one, is always a lowercase letter. So it is important that you write down your symbols properly and do the first letter as a capital and the second as a lowercase. Otherwise, it can change the meaning of the symbol. So as I said, elements are arranged in the periodic table from top to bottom and left to right. And they are not randomly arranged. The position of an element in the periodic table actually tells us a lot about the chemical properties. They are arranged by similar chemical properties in columns. So let's look at some common elements and their symbols. There are some symbols you want to get familiar with. Like, for example, let's start from the left here. Bromine is Br, calcium Ca, carbon, chlorine. So you see that chlorine is capital C, lowercase l. Chromium, cobalt. And so here, if you were writing cobalt with a C and an O all in uppercase letters, you could confuse cobalt with a carbon and an oxygen, because you can see here from to the right of cobalt, you see oxygen and it's capital O. So that's why it is important to do your second letter as a lowercase. Then we have copper, fluorine, hydrogen, iodine, lead. Lead is not an intuitive symbol. Pb is the symbol for lead. Pb comes from plumbum, which is the Latin for lead. Then on the right side, we have magnesium and manganese and molybdenum. Sometimes magnesium and manganese are confused, so make sure you don't confuse Mg from Mn. Nitrogen, oxygen, phosphorus, potassium. Sometimes phosphorus and potassium are mixed. P, capital P, is for phosphorus, and potassium is K, which is not intuitive, so you have to learn this one. This is one that comes up a lot. You want to know that potassium is capital K, and sodium is also not intuitive. It's also from the Latin. It's Na. Sulfur is S and zinc Zn. So you can look at them more on the periodic table. And so use that periodic table to select the correct symbol for each element. So you can pause the video and select your symbol and then watch the answer. So calcium is Ca, capital C, lowercase a. Sulfur is S. The other two symbols, Sl and Su, do not exist. Iron is Fe. As a French, the symbol here is meaningful for me because iron is said fer in French, which is F-E-R, and so that's easy for me to remember. But for you, you can see that iron has a symbol that is not coming easily from its name, so you have to learn that one. Sodium, we said earlier, it's Na, and this is really one you want to remember. Magnesium is Mg and not Mn or Ma. Let's do some more learning check here. You want to select the correct element name for each symbol. So again, pause the video before you watch the answer. So N is nitrogen, an element very common that you should remember too. P is phosphorus. It's very tempting to say it's potassium, but potassium is a different letter. Ag is silver. Ag comes from the Latin argentum, so that's why it's Ag. K is potassium. Krypton has the symbol Kr. And then F is fluorine. Femto is actually not an existing element. It's a made-up word here. So here is a periodic table, and it's color-coded. And the green elements are classified as metal. And so this classification between metals and non-metals is a very important one. It seems like not much, but it's actually something that will determine if you have ionic compound or covalent compound. So it's really something you want to remember well and think about when you look at the periodic table. So metals are represented in green. So they are located on the left side of the periodic table. Watch out, hydrogen in the upper left corner is not a metal. Hydrogen is a non-metal. Non-metals are represented in blue and located in the upper right corner of the periodic table. And then between the two, we have what we call metalloids, which means they are between metals and non-metals as far as their properties are concerned. And they are represented in orange here. There's only a few of them. So we know where they're located because they are sitting on the staircase, above or below the staircase that you see in more bold lines. So typically periodic tables have that bold line to help you locate where the metalloids are. Be careful here, aluminum and polonium are touching that staircase line, but they are not metalloids. Aluminum and polonium are metals. The symbols are Al and PO. Even though they touch the zigzag line, they are not metalloids. So let's go over those the classifications of metal, non-metal, and metalloids, and see what it means in more details. So metals first. Metals, we saw they are located on the left side of the periodic table. There were green ones in the previous slide. Metals are good conductors of heat and electricity, and I think you know this already because we use pots and pans in metals to cook, and the reason is because they can hold the food, but they also are a good conductor of heat, so you can cook in them. We use electrical wires, they are made of metals also. So metals, when you think of a metal, you think of a shiny solid, and because they are all, most of them are shiny solids at room temperature. There is only one exception, and that's mercury. Mercury with symbol Hg is a liquid at room temperature. This is the only metal that is a liquid at room temperature. And you may have seen mercury already in barometers, for example. It's very shiny. It's very heavy. If you were holding a barometer, you would find out. And so otherwise, when you think of a metal, it's a shiny solid. Metals are malleable, which means you can hammer them into flat sheets of metal. Metal are ductile, which means you can pull them into wires or pipes and tubes. Metals have very high melting points. So that's the properties of metals. Now, non-metals. So as the name says it, they have opposite properties of metals. So they are located on the right side of the periodic tables. In the periodic tables we saw earlier, it was the blue elements. So non-metals, they have a dual appearance. So contrary to metals, they are not shiny, they are dual. They are not good conductors of heat and electricity, so very poor conductor of heat and electricity. They have a low melting point and low densities. So metals, you can imagine them that they feel very heavy when they are in your hand. But non-metals, they are light in comparison. Their density is low. And they will melt more easily if they are solid. So non-metals can be found in the 3 different states of matter at room temperature. We find them as solids, liquids, and gases. For example, the solids are sulfur and carbon and iodine are found as solids in room temperature. Bromine is the only one that is a liquid at room temperature. And all the others are gases. So nitrogen, oxygen, hydrogen, chlorine, fluorine, and all the noble gases, helium, neon, argon, krypton, xenon, radon, are all gases. So that's the properties of nonmetals. And then there are the metalloids, which are located on the solid line that starts from boron and angles down towards astatine. So here the periodic table, the piece of the periodic table where you see them is shown. And so as their locations suggest, they have properties that are intermediate between metals and non-metals. And so most of them are also behaving as semiconductors, right? Semiconductors means they are sometimes conductors like for electricity, but not conductors of heat, like silicon and germanium. And it's a very useful properties to do any kind of electronics with them. So they are very handy, those metalloids. They are found in all kinds of electronic devices. There's very few of them. It's only 7 elements that are metalloids. First, there is boron, silicon, germanium, arsenic, antimony, tellurium, and astatine. And as I said earlier, aluminum and polonium, even though they are on that solid line, they are not metalloids. They are classified as metals. And think about aluminum foil. You know that's a metal, right? So don't classify aluminum as a metalloid. And polonium is the same, PO. So that's the properties of metalloids. So now let's do a learning check and classify some elements as metals, non-metals, or metalloids. And again, I want you to pause the video and do this classification before you watch the answer. So xenon is found in the last column to the right of the periodic table. It is what we call a noble gas, and that's a non-metal. Tungsten, W, the symbol W, is found in the middle left side of the periodic table, atomic number 74, and so that's a metal. Bromine, Br, is found on the non-metal side. It's what we call an halogen. It's very close to xenon that we saw earlier. Arsenic. Arsenic is a metalloid. It's sitting on that staircase line, and it's one of those metalloids. Cerium, symbol Ce. Cerium is found in the bottom of the periodic table in those two rows that are, below the main table. And it's the first element, atomic number 58. It's metal. So these are metals. And then aluminum. Aluminum, symbol Al, is found under the staircase, but as we said, it's on the metal side and it's not a metalloid, it's a metal. So as you know, we are made of matter, we are made of atoms and elements. And the four elements that comprises 96% of the mass of the human body are called the building block elements. And these are oxygen, carbon, hydrogen, and nitrogen. O, C, H, and N. They are the building block elements. And with those four elements only, many, many molecules can be made, organic molecules, and put together, they make tissues, and those tissues together make a human body, right? So we are made of those four building block elements for 96% of our mass. And so carbon, hydrogen, and oxygen are found in the four main types of biological molecules, which are the proteins, the carbohydrates, the lipids, and the nucleic acids. And then proteins and nucleic acids contain nitrogen. They're a bit more diversified by nitrogen. And then we have other elements that are important too. The first category is called the major minerals. Those major minerals are also called macronutrients. So these elements are present in a smaller amounts than the building block elements, and at least 100 milligrams of each are needed in the daily diet. So these are calcium, phosphorus, potassium, chlorine, sulfur, sodium, and magnesium. And so, for example, potassium, sodium, and chlorine are present in body fluids. Magnesium and sulfur are present in the proteins found in the muscles. Calcium and phosphorus are present in teeth and bones. So they are all very important for the maintenance of essential body functions. And then the trace elements, which are also called micronutrients. So they are called trace elements because they are needed in a much smaller amount. Usually less than 15 milligrams of each of these elements are required in the daily diet. And these, there is a list in the next slide, but an example, for example, is iodine. Iodine is necessary, for example, for the proper thyroid function. Iron is another trace element that is very important. It's needed in hemoglobin. Hemoglobin is the molecule that carries oxygen in red blood cells. Iron is also needed in myoglobin, the molecule that stores oxygen in muscles. So they also are needed for essential body functions, but in smaller amounts. And so this slide is summarizing the previous two slides. It reminds you of the building block elements, the major minerals, and then the trace elements. And here you have the list of the trace elements. And so yes, we need some arsenic, boron, chromium, cobalt, copper, fluorine, iodine, iron, manganese, molybdenum, nickel, selenium, silicon, and zinc. Okay, so you remember how we classified matter as pure substance, and a pure substance could be classified as an element or a compound. And so now we will go over what is a compound. A compound is a pure substance formed by chemically combining two or more elements together, right? So this time you bind elements together and you make compound. And so compounds are usually binding in set ratios, definite ratios. And so then you can give them a chemical formula. So the chemical formula will consist of the element symbols to show the identity of the elements forming the compound, and then subscripts to show the ratio of atoms in the compound. And so, as it says, subscripts, they must be written in smaller size on the lower right corner of the element. So for example, H2O, that's the formula for water. Water is made of 1 oxygen atom and 2 hydrogen atom. And so the subscript 2 belongs to hydrogen. You write the subscript after the element it belongs to. And the ones are implied. We never write the one when there is a subscript of 1, it's omitted. C3H8 is another formula. It's made of 3 carbons. The 3 belongs to carbon, and 8 hydrogen atoms. The 8 belongs to hydrogen. And so compounds can be drawn in many ways. We will learn that in chapter 4, for example. So if you look on the left here, H2O is the general formula for water. But if you want to show how the hydrogens and the oxygen bind together, you can use a ball and stick representation that shows the atoms as balls, and the stick represent bonds. And so the 2 hydrogens are bonded to oxygen there. Another way to represent molecules, and this is usually computer generated, it's not what we do on paper. It's called the space filling representation. And here you have the molecule of water represented in space filling representation. And in that representation, the molecule, the balls are closer together, and it's more realistic from that point of view, because atoms are, when they are bonded, their spheres overlap, and that's what creates the bonding. It's when the electron clouds overlap. And so this is more realistic of what a molecule of water would look like at the atomic level. And so the different elements are represented by different colors and by convention. Carbon is black. Think about your pencil lead. This is carbon graphite, and so that's black. Hydrogen is white. Oxygen is red. Red like blood when it's full of oxygen. Nitrogen is blue, like the sky. There is 80% of nitrogen in the sky, in the atmosphere above us, so blue. Fluorine is yellow. Chlorine is green. The chlorine gas is a green gas, also called mustard gas. Bromine is a brown liquid. Iodine is a purple solid. Sulfur is a yellowish powder. And phosphorus is represented as orange. So these are the convention for the colors. And that's the end of section 2.1.